Let's now discuss the first addition reaction of alkene, the hydrohalogenation reaction. So in the hydrohalogenation reactions, a hydrogen and a halogen, X, in this case X can be chlorine, bromine, or iodine, will then be added across the pi bond. And here is the schemes of a hydrohalogenation reaction. So here we have our alkene reacting with its X. And here in this case right here, H and X are then added to the carbon 1 and carbon 2. There are two possibilities where the hydrogen and the halogen may be added. We can have the halogen being added to carbon 1 and the hydrogen being added to the carbon 2, or the other way, where the hydrogen is added to the carbon 1 and the halogen is then added to the carbon 2. So these two products right here are different. And the question now is that which of this would then be the major products? So here in this lecture, we will go over these two products right here and we'll be able to determine for sure which of this product right here would then be the major products. And we will also go over the explanation of this as well. Now, so the mechanism of this hydrohalogenation reaction is as follows. So here in this case right here, we have a proton. This comes from a binary acid, so this it will be a very acidic proton. So this become almost fully positive. And it is then a great electrophile. When we react this acid with our alkene can now behave as a base or a nucleophile, in which it then donates electron to this proton, grabbing up this proton right here. So in this case, then the electron are then donated to a proton. In this case, the alkene is behaving as a base. And as the pi electron from the alkene are donated to the proton, either carbon 1 or carbon 2 would now become the carbocation. So we can either have this as the carbocation, where the hydrogen be added to the carbon 2, or we can have the hydrogen being added to the carbon 1, and now our carbon 2 will then become the carbocation. So here in this case right here, these are the two carbocation intermediates that we form. And now we have to ask ourselves this question: which of these carbocation would then be more stable? So here in this case right here, we have here a secondary carbocation, versus in this case right here, this is a tertiary carbocation. So clearly, this one would then be more stable. And therefore, the major products would then be the formation of this tertiary carbocation intermediates. And once we form it already, now our X now breaks up with the electron in it. And we can see that this is a good nucleophile. And it will then come in and attack our carbocation. So if this were to form, then it will come in and attack it, producing this product right here, where this halogen is added to the carbon 1. Now, although this is the major product right here, we will also form a minor amount of the product where we are producing this carbocation. And here in this case, the halogen can again come in and attack this one, although this is the minor products. And in this case right here, the halogen is then added to the carbon 2, forming this product above. So in this case right here, we will then see that this will then be the major product. It is the major product because it is the product of the more stable carbocation intermediate. And now this will then be the minor product. These products right here actually will refer to have some names associated with them, named after the chemist who discovered them. In this case right here, this major product right here is called the Markvonikov product. And the minor product produced down here is then called the anti-Markvonikov product. And that is actually the geoselectivities in the hydrohalogenation reaction. So it is called the Markvonikov rule. And in this Markvonikov rule right here, it basically is a description of the product based on the explanation that we have seen already. So Markvonikov, while studying this reaction, he observed the following. The hydrogen is then added to the less substituted vinyl carbon. And the halogen is then added to the more substituted vinyl carbon. So here in this case, if we are going to go back to our starting alkene, in this case right here, the carbon 1 and the carbon 2 are the two vinyl carbon. In this case right here, we can see the C1 is more substituted than C2. So based on Markvonikov, he described it as follows. The hydrogen again is added to the less substituted carbon. In this case, it would then be the carbon 2. And the X is then added to the more substituted vinyl carbon, in this case carbon 1. So that's how Markvonikov described the product, and that's what we have seen here. So therefore, this product right here is the major product, or we also call this as the Markvonikov product, because it follows this observation right here. And in the hydrohalogenation reaction, the Markvonikov is then the major product. So the Markvonikov is the major product. And the reason why is, again, it goes through a more stable carbocation intermediates. That's what we have seen already. So the explanation for this is actually not complicated. But in any case, we just want to describe this Markvonikov rule right here, so we are familiar with this terminology. Now, in most ordinary hydrohalogenation reaction, then the major product would then be the Markvonikov products. However, it will accidentally discover that when we perform this very similar reaction right here in the presence of a peroxide, such as hydrogen peroxide, or it can be any types of peroxide, even in small amount, would actually cause the HBr or the HX to be added in the anti-Markvonikov fashion. And this reaction right here undergo a radical mechanism, and therefore producing the anti-Markvonikov product. So if we were to perform this reaction, and our goal is to produce the anti-Markvonikov product, we will be adding some sort of peroxide, such as hydrogen peroxide. And we will be able to favor the anti-Markvonikov products. And the mechanism of this reaction is then as follows. So first, when we have some sort of peroxide, this is the structure of peroxide right here. And peroxide, in the presence of light, can break easily to become a 2 radical. And this radical right here then come in to react with HBr. So it come in and abstract the proton from HBr through the radical mechanism. And now producing an alcohol and the bromine radical. Once this bromine radical is produced, it then come in to react with our alkene. So here in this case, let's say this is our alkene. Our alkene would now come in to react with our bromine and creating a bond between this. So here in this case right here, the product can happen in two ways. We can now have a bond that come in where the carbon is forming a bond to the bromine, where this carbon on the terminal end is forming a bond to the bromine, or the other products in which that the bromine is now forming a bond to the carbon that is more substituted. But between these two, then one of this carbon would now become a radical. And as we have seen already, that the more substituted radical is then more stable. So therefore, the major product would then be as follows, where the radical locate on the more substituted carbon. So in this case right here, this is a tertiary radical, which is more stable compared to this other radical right here. This would then be a primary radical if it were to react the other way. And this is not as stable. So therefore, this would not be the major product. But the products is actually the one from above, where we form the tertiary radical. And now that we have formed this tertiary radical already, it can now come in and abstract another proton from HBr. So in this case, and our product. And now we are producing another bromine, and the next bromine thing can go and catalyze a next molecule react with the next alkene. So therefore, this is why that even in a small amount of this hydrogen peroxide, we can produce many of this bromine radical over and over again, and eventually all lead to this product right here. And this would then be our major product. And following the description from the Markvonikov rule, in this case right here, the hydrogen is then added to the more substituted vinylic carbon, and the bromine or the halogen is then added to the less substituted vinylic carbon. So this is why that this is then called the anti-Markvonikov product. So there we have it. If we want to favor the Markvonikov product, then we make sure we do not have a trace amount of hydrogen peroxide in it. And versus if we want to favor the anti-Markvonikov product, then we would need to add a small amount of hydrogen peroxide. And now let's focus on the stereoselectivity of a hydrohalogenation reaction. So hydrohalogenation reaction is actually not stereoselective. We will not be able to produce a particular types of stereochemistry that we want, but in fact we'll be able to produce a racemic mixture. And this actually make this reaction right here not very efficient in terms of yield, because again a racemic mixture is being produced. So here in this case right here, if we were to take this alkene reacting with HCl, then again the major product, in this case there's no peroxide present. So here in this case right here, we will then see that the hydrogen will then be added to the less substituted carbon, which is the carbon on the outside, this hydrogen, this carbon right here. And the chlorine will then be added to this carbon. And now when the chlorine is added to this carbon right here, this carbon will now become a chiral center. So therefore, we can now have the chlorine either pointing up or pointing down, or either R or S. And in this case right here, both of them will get formed. So we produce both this enantiomer, where this is now have the R stereochemistry, and we'll also be producing the other one. Right now, this chlorine is pointing in the back, and this would then be the S enantiomer. So we are producing a racemic mixture. And the reason why that there's no stereoselectivity in the hydrohalogenation reaction is as follows. If we were to look on the mechanism, so the first step going to happen is the base, the alkene acting as a base, come in, pick up this proton right here, kicking off the chlorine. So in this case, we'll be producing a secondary carbocation. This secondary carbocation right here will not undergo rearrangement, because it will it still will be producing a secondary carbocation if it were to do that. And in this case, that's what we would have right here. So in this case right here, this diagram, so one of it with then a hydrogen, to make sure we change that so that it will reflect this. But in this case right here, once we are producing this carbocation, this is now a secondary carbocation, and the hybridization of this carbon is now becoming Sb2. And in fact, that's what its structure would look like. An Sb2 carbon with an empty p orbital on it. And when the next step, where the nucleophile come in to attack this electrode, this carbocation right here, the nucleophile can either attack from the top or from the bottom. In this case right here, there's really no preference, because this is an achiral intermediate. So in this case right here, there's both the top and the bottom are equally in terms of steric hindrance, and therefore both would happen. And if we're to attack from the top, then now we produce this product. If we're to attack from the bottom, we're now producing this product. And these two products right here are mirror images of each other, or they are enantiomers of each other. And thus, we are making a racemic mixture. And as I briefly mentioned earlier already, carbocation rearrangement. So in hydrohalogenation reaction, if it is possible for the carbocation to rearrange to produce a more stable carbocation, then yes, it will happen. So the XX addition are subject to carbocation rearrangement. And when they can occur, they do occur and will occur. For an example, if we were to have this alkene reacting with HCl, so here in this case right here, the first thing going to happen would then be the alkene acting as a base coming to pick up the proton. And again, the hydrogen will be added to the less substituted vinyl carbon. And now we are producing this carbocation. And this is a second carbocation. And in this case right here, it is possible for us to rearrange this carbocation to produce a more stable one. In this case, it will then undergo a 1,2 hydride shift. And where the hydride come in to attack this. And now the product that we would then be producing would then be as follows. And once you form this already, the chlorine can come in to attack this and therefore producing this product. Now we will also observe the other product in which it does not undergo the carbocation rearrangement, where in this case the chloride will then come in and attack this. And producing this product right here. So both of this product will get formed. However, the product from the carbocation rearrangement will then be the major products. And the yield of this reaction has been found to be 60% and 40%. Favoring slightly shifted toward the rearrangement products. So this is the rearrangement products. So again, both will get formed. However, the major product is the product of the rearrangement. And in summary, how the hydrohalogenation reaction proceed with reduced selectivity. And again, we can either produce a Markvonikov product or the anti-Markvonikov product. And in most traditional hydrohalogenation reaction, where we make sure our reaction is our flask is very clean and we do not have a trace amount of peroxide, then we'll be favoring the Markvonikov product. And the Markvonikov product is where the halogen is added to the more substituted carbon, the vinyl carbon. Versus if we want to favor the anti-Markvonikov product, then we will have to add a small amount of the peroxide in it. And there's no stereo selectivity in the hydrohalogenation reaction. And there will be carbocation rearrangement in hydrohalogenation reaction if it's possible for the carbocation to be arranged to produce a more stable carbocation. And now let's try some of this problem right here. So predict the major product and draw the reaction mechanism. So in this case right here, we will then see the hydrogen and the bromine will be added to the double bond. And in this case, the bromine will be added to the more substituted carbon. So that would be this carbon right here. And the hydrogen will then be added right here. And the bromine will be added right here. So when we draw the product, this will be the product right here. And this would then be the Markvonikov product. And on the reaction number 2, so here in this case right here, we are taking this alkene reacting with HBr in the presence of peroxide. So the major product would then be the anti-Markvonikov products. So make sure we take notice of this before we write out the product. So in this case right here, this is anti-Markvonikov, so that means the Br will be added right here and the hydrogen will be added right there. So make sure we know how everything works out before we draw the structure of the product. So here in this case, that would then be the product. And as for number 3, this is very similar. So in this case right here, we have HBr and there's no peroxide. So the major product would then be the Markvonikov product. So therefore the bromine will then be added to this carbon and the hydrogen will be added right there. And now, but in this case right here, it is impossible because we have to now take notice that once we are producing in the mechanism of this reaction after the basic attack, this carbon will become a carbocation. And now it is possible for this to rearrange. So therefore we have to think about the rearrangement product as well. So in this case right here, let's draw the product without the rearrangement first, and that would then be our minor product. And that is where we would then have the following. So that would be this product right here, where the bromine is added right here. But then we know that this would then be just a minor product. So this is without the rearrangement. Now the major product would then be the product of the rearrangement. And to draw the mechanism of it, this is how it would go. So first, the basic attack. But the hydrogen would then be added to the less substituted vanilla carbon. And now we are producing a secondary carbocation. And here in this case right here, it is possible to rearrange because nearby there is a hydrogen on the next carbon. And it is possible to rearrange to form a more substituted carbocation. So in this case, it will do that. And now there will be another hydrogen right there, and now we're producing a tertiary carbocation, followed by the nucleophilic attack, where the bromine will now come in to attack this and producing this product. So this would then be the major product. And this would then be the minor product. Okay, please try number 4 and number 5.